Welcome back to multivariate calculus. In this video, I'm going to be introducing you to iterated integrals. As we've seen in our study of functions of several variables, there are a couple of different ways that we can consider the idea of a derivative. There's a couple of different ways we can generalize the derivative into that several variable function. And so because of that, there are also several ways that we can generalize the integral into functions of several variables. The iterated integral is probably the most straightforward. Let me get my head out of the way, and let's start with area in the plane. You have seen in your previous study of mathematics that if you have an arbitrary region in the xy plane bounded above by some curve y equals f of x and bounded below by some other curve, say y equals g of x, you can find the area here by collimating and finding the area of all of these infinitely many rectangles and adding them all together. You get a formula that looks something like A equals the integral from A to B, and I just realized I never put in my A and B here, of f of x minus g of x dx. All right, fairly straightforward way of calculating the area between two curves. But we want to do this in a multivariate sort of way. And so instead, if I take the same picture and I just get rid of that blue area component that we just looked at, and instead just think about any one small rectangle. Well, any one small rectangle is going to have a length, and if it's small enough, we can call that length dx, and it's going to have a width, and if it's small enough, we can call that width dy. And so, in a multivariate calculus sort of way, we can find the area of this little bit. I do want to mention, I'm always going to use capital A for area because that's the way that I learned it. But there are a lot of calculus textbooks and a lot of applied science textbooks that build on calculus that instead use little a for area just to make things confusing. It doesn't really matter. The variable is what it is. But in general, my area of this region is the integral over the region of that little piece of area. And because area is a two-dimensional structure instead of just a line, as we're accustomed to dealing with integrals, we often put a double integral symbol. Right? So it is the doubled integral dA, because that tells us that we're talking about two-dimensional structures. Right? We're integrating over areas, not over lengths. When we get to integrating over volumes, we'll put a third integral symbol on it. But we can calculate this area The area of that infinitesimal rectangle is dy dx. And then the great advancement in multivariate calculus which was conjectured and used without proof for quite some time, but eventually Fubini was able to prove that this has to work, so it is called Fubini's theorem. And Fubini's theorem tells us that we can just integrate separately. Where do my y coordinates range? Well, at the top, y is equal to f of x, and at the bottom, y is equal to g of x. And now here's where things can be a little bit surprising at first glance. Because when we integrated with respect to y, we've already taken care of the upper and lower possible constraints of this problem, we don't have to worry about each little bit horizontally being a different length. Instead, we can just look at the overall extents in the x direction. And we can integrate this from y equals a, or I'm sorry, from x equals a to x equals b. Before I go any further, I do want to introduce a quick notational shortcut. I very often put these equations in my indices of integration, because as we'll see as we move onward, we're going to learn ways of switching things around and changing the order of integration, and it can become easy to make a mistake where you forget which limits of integration go with which variable. But most mathematicians, and especially most physicists and engineers, say that writing x equals and y equals is entirely too much work. So you would instead see this written as the integral from a to b, the integral from g of x to f of x, dy dx. And if you want to write it that way, I actually encourage you to do so. That is the more conventional standard. But I don't write it that way because I learned when I was a student pretty quickly that whenever I tried, I made mistakes. So I started adopting this of I put the equation every time I write limits. It helped me stop making mistakes. And I'm going to keep doing that because making a mistake when I'm a student is problematic. Making a mistake when I am a practicing mathematician is annoying. Making a mistake when I'm trying to show you how this works is a lot worse. I will still make mistakes, but at least this is one way I can try to limit the mistakes that I make. Right? Math is hard, and making stupid little mistakes is just how it goes. Taking your time, being careful, and looking for ways to force yourself to slow down are the ways of preventing making mistakes. Right. Anyway, back to the integration. The amazing thing that Fubini was able to prove is that in this integral, we actually have two integrals at once. If I just insert some grouping symbols like this, what do we have going on inside of those parentheses? We have the integral for limits of integration on y of dy. The integral of dy is just y, and we'll put in our limits of integration from g of x to f of x, and then we will surround it with the stuff that was outside of the parentheses. Then we will use the same process we have used for several courses now on evaluating a definite integral. The fundamental theorem of calculus says we evaluate y at the upper limit, f of x. We evaluate y at the lower limit, we get g of x, and we subtract those. And that should look very familiar to you, because that's the same area integral that you learned in your study of calculus of a single variable. Nothing new is happening here, except that we have introduced some new notation. But of course, we can't just stop there. Now that we have this new notation, it had better be useful for something, right? Mathematicians can invent new notations till it's coming out of our ears, but unless it's useful for something, there's no value in it. We just find the most efficient notation and we stick with that. In this case, having this notation allows us to approach the volume under a surface. The same basic idea as the area under a curve. In general, remember, calculus of a single variable, the integral from a to b of f of x dx if we have limits of integration are points here, and we sketch in the curve y equals f of x, then the integral gives us the area between that curve and the x-axis. Now we can take this idea and we can extend it into two dimensions. The integral over some region of f of x and y dA. All right, let's see if I can sketch this out in a way that's actually readable. All right, as you have at this point become very familiar with, trying to explain and draw a region in three-dimensional space is incredibly challenging. But let's assume that we have our region down here in the xy plane. And then we have some surface floating above it. Well, we can project our region up to create this cylinder-looking thing and calculate the volume of that using the area integral, the integral in two variables. So let's look at a relatively simple example. Here I have the integral over a region of y squared e to the x dA, and my region is going to be a rectangle. X is between 0 and 1, y is between 0 and 2. If I sketch out my coordinate plane, come on, there we go. The region that I'm trying to integrate over is a very simple rectangle, and that's a great first example because it means that my limits of integration are going to be very simple. All right, so using Fubini's theorem, I can rewrite this as an iterated integral. We will have the integral x goes from 0 to 1 of the integral y goes from 0 to 2 of our function y squared e to the x dy dx. It's not as apparent at first glance what's happening here. But if you take a little bit of time to think about it, this should make sense. Again, we have iterated integrals. We can think about the inner integral and then think about the outer integral a little bit later. And I'm going to write this out in a couple of steps here. Once you understand what's going on, this whole process is going to be a single step. Right? I would just look at this and write out, I'll tell you when we get to the end. Right? But the first thing I notice is inside this integral, everything is being integrated with respect to y, but then I have this e to the x. And just like with partial derivatives, when we're dealing with iterated integrals, we're going to assume that x is constant with respect to y. So I can bring this out of the integral. Letting me rewrite the whole thing like this. And again, I'm going to focus on the inner integral. Integral from 0 to 2, y squared dy. And now here's something that we did not have in the first example. Because my limits of integration are constant, and x does not appear in the limits of integration, in the integrand, anywhere in here, this entire integral is constant with respect to x. I can bring that whole thing out of the integral. I can have the integral y goes from 0 to 2 of y squared dy, and then the integral x goes from 0 to 1 of e to the x dx. These are two completely separate integrals, which means I can evaluate them independently and then just multiply together the result. This doesn't often happen, but being able to recognize when it does and take that original integral and rewrite it in this form all in one step saves you a lot of time and a lot of paper. All right, but now we integrate. The integral of y squared is 1/3 y cubed. That ranges from 0 to 2. The integral of e to the x is e to the x. That ranges from 0 to 1. All right, so we evaluate. Let's see, 2 cubed is 8. So I will have 8/3. 0 cubed is 0. E to the first is e. E to the 0 is 1. A couple of different ways we could write that out. I'm going to go with 8e minus 8 all over 3. If this was an integral that appeared in an application in an applied mathematical science course, you would then grab out your calculator. E is about 2.7. 8 times 2.7 is about 22. 22 minus 8 is 14. 14 divided by 3 is just shy of 5. Right? You could use a calculator, get a better decimal approximation, but this is a math course, and in a math course, 8e minus 8 over 3 is considered a better way of writing it, for whatever reason. All right. Onward to the next example. Here, once again, we have a rectangular region. Y goes between 4 and 6, x goes between 0 and 3, and we have the entire rectangle, nothing strange happening there. In our integrand, however, we have subtraction. And the one frustrating thing about subtraction is that you can never factor anything out when you're subtracting. So as we rewrite this as an iterated integral, x goes from 0 to 3, y goes from 4 to 6, we really do have to think about the whole thing when we do the first integral. Right? There's no way of getting rid of the x from the integrand in order to separate this. All right, so y squared minus x squared. Integral of y squared is still 1/3 y cubed. Integral of x squared. Well, x is a constant with respect to y, and the integral of a constant is that constant times y. So I'll have x squared y. Right. This is one of the places where I am the most prone to making mistakes. So taking my time, being careful. We are evaluating the limits of integration for y, marking in y equals. Not standard, that's not the convention, but I find that it's helpful because it prevents me from accidentally plugging in the value to x instead. X is a constant, it's just x. Y changes, y takes on the limits of integration. All right, we'll have 1/3 times 6 cubed, 216. And then we will have 6 times x squared. Right? 4 cubed is 64. And then simplifying a little bit. 216 minus 64 is 152. -6 minus -4 is -2. And we're still integrating with respect to x. At this point, it is down to the kind of conventional integral in one variable that you've studied in your previous study of calculus. Nothing crazy going on here. Antiderivative for a constant is that same constant times x. Antiderivative for 2x squared is 2/3 x cubed. Evaluate at our limits of integration. We end up with 152 over 3 times 3 is 152. 3 cubed is 27. 27 divided by 3 is 9. 9 times 2 is 18. And then plug in x equals 0, we get 0. So finally, 152 minus 18 is 134. This is one of the rare problems in calculus where I kind of wish I had a calculator next to me because I'm 99% confident in my arithmetic, but some of those numbers were a little bit crunchy. I do not expect that you have this kind of arithmetic that you can do off the top of your head. I expect that you're going to be using a calculator to double check and make sure everything is working fine. I have spent entirely too much time around these numbers, and a lot of things have gotten stuck in my head that I kind of wish I could get rid of. But however we get it, we do get to our result here. 134 is what I have. I hope that that's correct. And let's go to one more. This time we get a little bit of trig involved. Function of x and y, x sine y plus y cosine x. And our region of integration here is going to have x going between 0 and pi over 4. And y going between 0 and pi over 3. The actual mechanics of the integral are a little bit more challenging in this one than the ones that I went through. But now that you understand the process, those challenges of integration are the same things that you've been doing in several previous courses, and I'm confident that you can get through it. Take a couple of minutes, see what you get on this one, and I'll see you in the next video.